Interested to do that more. Couldn't find time in my day job to do it. So I left the job and trying to make more time for open source. Really great to be at the summit and learning all this stuff from everyone. So to jump in, maybe most people have run into this. I ran into it pretty quickly when I started using Dask. I guess there's many things to Dask. I went straight for the data frames and the arrays and ran into the lack of an implementation of iloc, which is a feature in pandas data frames that lets you slice by integer indices. So the main, there's like some plumbing that tracks like how big every partition in a data frame is that does not exist and is necessary in order to implement iloc. So I've worked on implementing that, basically adding it to data frames wherever they're created, propagating that information through whatever data frame transformations I can figure out a way to do it for. Some shuffles and things, you're just like, there's no way you're going to know. If a user passes like filters the data frame rows by something that's only going to be known at runtime, like just give me all the prime numbers from a series full of integers, right? There's no way that statically at graph construction time, you're going to be able to know that. So sometimes you're just lost. We'll just won't have this information. iloc will remain unimplemented. But for my hope and what I'm trying to prove out is like in a lot of cases, we can track this and we can have this feature for well-behaved or like a lot of like mainstream kind of usage of data frames. So there's a giant PR that I opened last September and Tom was sort of like, cool, thanks. This is a lot. Like, this will be the start of a journey for all of us, I suppose. And I'm really appreciative of how patient all of the committers have been as I've like let this thing bit rot, kind of rewritten it, and I've had to do all this Git plumbing to like manage this thing. It's kind of sort of like a whole other talk about all the Git tooling that I've ended up like writing just to like take this giant. I kind of like built the whole thing, got it working, and I was like, I have to pull. There's like 4 or 5 or 10 different pieces of this that should logically be like factored out, cleaned up, reviewed on their own, rather than just like a big blob that surely has lots of bugs and no one can really review. So yeah, I've got some PRs here that have been factored out. Some of the things like along the way of implementing the feature, I made improvements that are like mostly unrelated, but then my actual implementation of iloc ends up using those things. So like I could go back and write iloc without that, but like it's like they are sort of dependent. It's kind of the easiest path to getting everything merged. But a lot of questions about the sort of like the subset of logical features within this thing and which parts of the power set of those features need to go in what order and stuff like that. Trying not to leak all that complexity to all the reviewers and to the whole code base, but it's been fun to deal with. If anyone's really curious, you should be able to find the links to all the relevant stuff here from the PR or from the slides that I have a bit.ly link here for. And just real quick shout out, like I've been supported in most of this work by Celsius, which is a single cell RNA sequencing drug discovery company that's really interesting. And they're looking to use Dask in the single cell space. They are using it hitting some of these pain points, and I've been working with them to try to fix them in a directed way for what they're after. Okay, so just to I kind of went all the way down into the weeds there a bit, but scoping the problem at a high level again. Dask arrays know their chunk sizes, like literally the integer number of what the dimensions are of every chunk. Data frames don't know that, and that's the main missing piece for implementing iloc, where you want to say, give me entries 100 to 200, and data frames know their divisions, which is like the boundary element values. But those can be, that's not necessarily just like sequential integers that are enumerating the rows of the data frame. It can be strings or anything that's not, that doesn't actually, it doesn't really help you to implement iloc or to be able to slice by integers. So this is kind of the approach that I took, was first like forgetting about iloc, there's sort of this question of like, what if data frames knew how big their chunks are, right? And so I just added a field to data frames. I populate it at all of the input places where I can figure out how to, in some cases it's very easy, like from pandas, you have the pandas data frame is in memory. And so you just kind of chunk it up yourself. You know the sizes of each chunk trivially. If you're coming from a Dask array, you know those chunk sizes. HDF5 and Parquet often will usually know the chunk sizes. So we start out by populating this in as many data frames as we can, and then depending what is done, we try to figure out how to either. So a lot of times, if it's a simple transformation, like just a straightforward map or apply, where the number of rows in every chunk is not changing, and that's easy. You just pass it through. In other cases, we have like joins and stuff. It's like if the things are sorted in a certain way, you can be like increasingly clever and try to recover more and more of these cases. But starting from a baseline where data frames are just like assumed to not know this information, you can sort of drop in an implementation of iLoc that uses this if it's there. And it can do the same not implemented error otherwise. So that's what I did. Here's like, a little bit of information about how the different hoops I've had to jump through to try to structure this thing so that like the logical pieces are pulled apart in a reasonable way. On the left in the background here is just sort of my whole commit graph history, but just looking really quickly at the graph on the right, which is a simplified version. You have like, I just rebased this whole stack last night after 5 weeks of letting it bit rot. And that's like, and I've had to do that a couple times, and it's like pretty terrifying, like sit down and be like, oh man, I put all this work in this thing. It's like dangling. Life got in the way. I haven't finished it. And now I'm gonna have to do all this work just to keep it afloat, right? But I was able to, a couple hours last night, I was able to get it all rebased and current. So I've built off of the latest Dask release. There's a few commits on main since then that I'm also rebased on top of. And then I have this whole structure of branches that mean different things and build on each other in different ways. That's downstream of that. And that whole structure is what I'm like rebasing and just pushing a snowball down the commit history a little bit. So I've got like a couple PRs out. This one, divisions, it's like just some bookkeeping around making sure there's never empty partitions, which are manifest as like duplicate divisions. There's a couple code paths where I found that can happen. So that was something that was originally in my giant ball of code, and I factored it out. It's like sort of necessary, sort of not, this sum2 branch, it's like has some stuff related to just dealing with sparse matrices and NumPy matrices, not to be confused with ND arrays and SciPy sparse matrices as the blocks of Dask arrays. That's actually totally orthogonal to the iLoc work, but just because I have, tests and things downstream. All of my iLoc stuff is up here. I make like, I have this like stack of branches that are P0, P1, P2, etc., all the way to PS, which originally stood for partition sizes. And that was kind of like the endpoint. And there's like 80 commits along this route. And then I've been maintaining these like parallel branches that start with a queue that correspond to some checkpoints along the way and have all the commits squashed. So that's in the background here. You can see just like, it's like 12, like 12 commits, Q0 up through QS. And each commit is actually a squash of like, 8 or 10 commits from the P branch side, where I have like a more granular accounting when I'm rebasing. Sometimes it's better to have the option to have it more granular and then have these like squashed versions on the side. Anyway, a million things we could talk about that. I won't take more of your time. This is what the Git history of the P branches looks like. This is like the whole thing in all its glory. It's like 80 commits. And these checkpoints they don't necessarily correspond to like the most logical bits of functionality. They're just like places like for my own, ability to track this stuff. I was just like, let me make sure that I basically have the GitHub actions and the CI passing at every one of these checkpoints, so that we can break it apart. We can merge like bits by these prefixes of the larger work can go in and sequence, and it can be a little more manageable for the reviewers. So this is like last night, I rebased all these, like, I don't know, several dozen branches that, build on each other. And I just kind of force push them all to GitHub. I let GitHub Actions just go nuts for like 5 hours. Usually just waiting on the Mac OS instances, which are like, the most scarce, I guess. But you get this like commit history on GitHub where it's like you get at least like these green checks along the way, so it's not like a totally unaccountable mess of commits. So yeah, sorry, I'm way over time. Some next steps are really just getting this stuff merged. I'm making more time in my life to actually get this stuff over the line, and looking forward to getting it merged, hopefully. And really appreciate all the reviewers' help and patience with this, and I'm excited to try to get this contribution over the line. So happy to take questions maybe at the end or in Slack or whatever. Thank you.
All right, thank you very much. Our next key fact is that honeybees live in colonies, and within any given colony, there is a single queen, potentially tens of thousands of female worker bees, and several male drones. All right, our next speaker is Idamar Turner-Tari. Sorry if I messed up your name.
And just for people who join us a little bit later, why are we doing BFACTS today?
Today is World Bee Day.
Yeah, all right. So let's keep our BFACTS going. Yeah, we'll use the Slack channel as well for two purposes. One, for speakers, if you want to share anything with people on the Zoom here. And then if people have any questions, we can post them there. And if we have time, we'll answer them, or we can answer them on Slack. So use the Lightning Talk Slack channel for that.
So can you see my screen?
Yes.
And you can hear me, I guess. Okay, so today we're talking very briefly about FEEL, which is a Python memory profiler for data science and scientific computing, which is to say the kind of things people use Dask for. So high memory use is an expensive problem. If you run out of memory, your program dies or becomes vastly slower as it starts swapping. RAM, you can spend money on the problem, but RAM tends to be more expensive than CPU. And so it's, at some point, you're going to want to reduce the memory usage of your program. And in the kind of things you're using Dask for data processing, where you load data, process it, and then write out a result, memory usage is often very spiky. So like a web server, if you have memory usage problem, it's a memory leak. That's not what data processing suffers from. It suffers from loading a large chunk of memory, doing something with it, and then throwing it away. So if you want to optimize your memory usage, what you care about is reducing the peak memory usage. If your program uses 1 GB most of the time and then spikes 10 GB is how much you need to be available on your hardware. So that's the bottleneck. That's the thing you have to optimize. So you need to reduce the peak memory usage. So if you're going to be measuring memory usage, you need some tool that will help you figure out peak usage and where it's coming from. And FEEL, F-I-L, is a memory profiler, an open source memory profiler specifically for that use case. And in particular, it can track memory allocations from Python, but also any third extensions you have. So Python, C++, Rust, Fortran. A little iffy on Fortran, but I've tested it, seems to work. The idea is any memory being allocated by your program, it should track for you. It's also designed to be really easy to use. So if you're running your program by doing Python example.py myarg, to run with a FEEL, you just do FEEL profile run example.py myarg. So you just change Python to FEEL profile run, and it should run your program and profile it for you. It also has a Jupyter plugin I'm not going to show here, just to go through things quickly. So here's an example output of FEEL. And so you can see it tells you the peak memory usage. So in this case, 566 megabytes. And the output it gives you is a flame graph. And so flame graph is a way to show performance information, in this case, memory usage. And the width of these frames here is a percentage. So all the way at the top, we start at 100% of the memory. And we see that about 28% of the memory went down this code path, and 70% came from this code path. And you can look at the width, but in FEEL specifically, I've made it so the redder the frame, the more saturated it is, the more of the memory it uses. Just looking at this visually, you can see that most of the memory is coming from this part of the code. And I can click on it, and now you can actually just see a stack tray. So you can see 70% of the code was allocated by this particular stack trace. So by line 16, an example.py, calling line 14, calling line 5, allocating this large NumPy array. And you can see here that another 14% came from this line of code, and I can click on it and see a stack trace. Another 14 came from this line of code. You can also see here, you can see how this part of this function, this code path, created 2 arrays, which use the rest of, which each use about 14% of the memory. So you get a really clear view of what the peak memory usage was and which lines of code were responsible and how what code path brought you that point. And so once you know this, you can say, oh, 70% of my memory is coming from this stack trace. I should figure out how to optimize it and reduce memory usage. There's some limitations. Notably, it doesn't support multiple processes. So if you're going to use it, when using it with Dask, you have to use either a single threaded or multi-threaded scheduler. Dask Distributed won't work. The multi-process scheduler won't work. So there's no multi-process support. There's definitely no multi-host support. There's no DSU support, GPU support at the moment. And there's some performance overhead. And I've spent a bunch of effort to make it not terrible. So it's maybe like you're running at 60% of normal speed. And so for profiling purposes, for debugging your program, that's actually quite usable. It's not that bad. You probably don't want to use it in production. I'm working on a version that will work in production by having very small memory, very small performance overhead, trading off in accuracy. If that interests you, let me know. Again, it's an open source memory profiler. I guess the other limitation is it doesn't work on Windows. It's Linux and Mac OS only. You can find it at pythonspeed.com/fil, also on GitHub. And if it doesn't work for you, if there's other features you'd like, I'd love to hear from you. It's always great hearing from users. And that's it.
All right, thank you very much. If you just joined us, today is World Bee Day. Your next bee fact is that honeybees have been cultivated for at least the past 8,000 years, evidenced by cave paintings in Spain and depictions of honeybee hives in Egypt. All right, in hieroglyphs. All right, our next speaker is Doug Davis.
Okay, yeah, let me know if you can't see my screen share, but I will go ahead and get started. So yeah, today I'll be talking about Dask histogram. The notebook that I'm using here for the lightning talk is available here at my GitHub/Dask Summit 2021. I'll link it in Slack afterwards. So first, I would like to start by very briefly talking about Dask.array histogramming. So Dask.array provides histogramming via the NumPy interface. So just right here, I'm importing Dask array, making a standard normal distribution with 4 chunks. So we can see it here, 4 equally sized chunks. If we pass this to dask.array.histogram, we get an array of counts and an array of bin edges returned back to us. And here, nothing has happened yet. We just have this final array, a lazy array. If we compute it, we get the total number of entries in each bin. And we can also visualize what happened while this happened, during this. So we started with our standard normal distributions, 4 chunks. A histogram was created on each chunk, and we had a final aggregation here at the end to get this final array. So that's what's going on just from the Dask.array module. Now, leaving Dask world, now I'd like to spend a minute talking about the Boost histogram library. So there's a number of people from the high energy physics community here at the summit. Boost histogram is a library that's been spearheaded by the high energy physics community, where really at the crux of it, histograms are more than just arrays. And so Boost histogram provides an object-oriented API for doing histogramming with Python, and also some additional tooling around it, which I'll talk about in a bit with the hist library. So if I import Boost histogram here and import NumPy, remember I've left Dask for a second, just talking about Boost histogram, I can make a couple of a few arrays here. So one array for an X dimension, a Y dimension, and a weight for each XY pair. So make those pieces of data. And now I can use the object-oriented API to create a histogram. I create the histogram by defining a couple of axes. You can read the Boost histogram docs for more here, but really the histogram is defined by its axes and how the data is stored via the storage. So here I'm going to use a weight storage because I want to keep track of the variance in each bin. For example, the API provides this. So I create the histogram. There's nothing in it. I just have a histogram object. Then the fill method is where I pass in my data and the weights. And now I have a filled histogram. One of the nice things about Boost histogram is it provides the familiar NumPy API inside this Boost histogram NumPy module. So you can call, since I have 2D data here, the histogram 2D function, which is comes from NumPy. And because I want to get an object back, I just use this histogram keyword argument. And in this case, I'm doing the exact same thing I did with the object-oriented API, but now just doing it with the array function API. And if I look at the bin counts of each of these, they're exactly the same, H1 and H2. So Boost histogram just gives this object-oriented API to do more with histograms than NumPy provides. On top of, built around it, is this hist library. So now I'm going to import hist, pass my Boost histogram object to this additional higher level API called from hist, and now this is more of like an analysis front end. And so there's it has built-in Jupyter Notebook support. So this is something that you get kind of for free from using the Boost histogram API, is this additional layer for analysis. And so there's more functionality here. I can do more plotting since I have a 2D histogram here. Look at everything going on in 2 dimensions, project it to one of the dimensions and look at it. So it's a nice analysis layer. So now let's go back to Dask and combine it with Boost histogram. So here, we can build on top of Boost histogram to provide an object that is lazily fillable with Dask collections. So now I'm going to create exactly the same data set, but now with Dask and a little bit larger. Still just like some random distributions in X and Y with some weights, but now no computation has occurred. These are not materialized. This is just lazy Dask data. Create a Dask histogram. Again, once I create the object, it's empty. Now, the main difference here is when I fill it, I'm filling it with Dask collections. Again, nothing happens because we're in the Dask world where we're just lazily setting a task graph up. So now the repr for Dask histogram says I do have some staged fills, but if I call it empty and has staged fills, I get true here. And now we can visualize what's going to happen if we were to compute this histogram. It's very similar to what we saw before with Dask.array. Here we have multiple dimensions, so we have a few more nodes, but we just have a bunch of distributions, each chunked properly. And on each of these sets of chunks, we're going to compute the histogram and get an aggregate in the end. So if we compute this, now we have exactly what we had from the normal Boost histogram API. We just now have data is behind this object. And again, we can pass it to hist. So this is what you get by with Dask histogram mimicking the Boost histogram API, this additional analysis layer. So finally, the last thing I want to talk about is a small multi-step example where we're stitching together a task graph with help from Dask.delayed. And Dask.delayed is used quite a bit in the back end of Dask histogram. So here we have 2 functions. We have lazy data factory. Just imagine this is something where you're pulling data from, but you're not materializing it immediately. We want to form a task graph. And we have a function called save histogram that will store the eventual final histogram to disk. So let's get those functions loaded. Let's go ahead and wrap save histogram in delayed. So we could have used the decorator here on save histogram, but just for completion's sake here, go ahead and do it explicitly. So now we have a lazy save function. So I can load the data, which is going to give me like something I want to histogram in 3 different weight variations. So let's say I ran some simulation, but I'm not sure about how the simulation works, with absolute certainty. So I've got some variations in there and I want to do some study. So I'm going to histogram this data 3 times with different weight variations. So I'm going to use the functional array-like API here called Dask histogram.histogram, but I'm going to use my different weight variations. When I create these histograms, I'm then going to pass each one to my lazy save function after converting the histogram to a delayed object. So when I call this, nothing has happened yet. I've just set up a task graph that we can now visualize. So here we have our distributions going and each getting they're going to get histogrammed on each of their chunks, finally get aggregated, and after they get aggregated, saved. And so after I compute this, now here on the side, I've got some pickle files where the histograms were saved, and I can go ahead and load these and plot them later. So that's Dask histogram. It's a young but usable library. Testing is very welcome. It just takes the Boost histogram library and makes it compatible with Dask collections. And it's not just arrays, it's compatible with also Dask data frame. You can pass in columnar data from a data frame or series, things like that. So yeah, please, if you're interested, give it a whirl. And I'm happy to chat with anybody about it, Slack, after the summit, whatever. Yeah, that's it. Thank you.
All right, thank you very much. Today's World Bee Day, and I have some bee facts for you. The queen can lay either fertilized or unfertilized eggs. She chooses which to lay based on the size of cell she needs to lay in. A drone cell is wider than a worker cell, and she'll lay fertilized eggs in the worker cells and unfertilized eggs in the drone cells. And I believe the next speaker is Martin Durant. Thank you.
Hello, you can see my screen?
Looks good.
Okay. Reference file system. This is a strange concept for most, but I'll go through this with a little bit of example, so I hope I don't take too long. Quick introduction. There is a lot of data out in the world that is in various archival formats along the lines of HDF5, which is pretty ubiquitous in large data array for long-term storage in archives produced by various scientific institutes. But since we're working at a Dask meeting here, we know that the cloud is a thing and you would like to do your compute in the cloud. In particular, you want to be able to access your data in parallel and seamlessly. And that's something that, for example, Zar is really good at. It's not the only one, but it's something that I happen to be involved in, so I mention it. Now, if you want to use the nice features of something like Zar, but what you happen to have is HDF5, then maybe you would want to copy and rechunk it into some other location. And that's something that the Pangeo Forge collaboration is trying to do, for example, build recipes of new data sets. But it does mean that you end up making a copy of your originals, and that requires resources. So a reference file system is an alternative to doing that. And it works something like this. Here is an HDF5 file layout. It has some metadata and it has some chunks of actual binary data. This binary data will be in usual C layout, so big arrays, plus some encoding and compression on top of that. But the metadata might be scattered throughout the file. So the thing that we're going to do is we're going to look through this HDF5 metadata and figure out where the chunks are. And we're going to construct a pseudo Zar data set, which is going to point to the binary chunks, and it's going to refer to them using a file naming convention that Zar understands, so that it can interpret this whole data set as a Zar data set, but without copying any of it. And that's essentially what reference file system does. And you can go further than this. In fact, if you have several HDF5 files, then you can go one stage deeper and figure out where each of the chunks of each of those files might fit into one global ensemble data set, and Zar will be able to read this. So there is an implementation called reference file system. It lives in FSspec. FSspec is a project to provide a single user interface over many different storage backends. So reference file system is now one of those backends, and it can in turn read from any other FSspec backend. And it provides parallel access and concurrent IO, at least if the backend supports it. So that is for things like S3, Google Storage, Azure, all of your favorite cloud storage backends. And it has some extra features to make all of this work nicely. And I can demonstrate at least a couple of these in a moment. The last one is particularly interesting of these bullet points here. I won't go through all of them, which is the ability that if you have small file-like things, and this is particularly the little pieces of ZAR metadata, you don't have to store those separately. You can inline them into your references so that the lookup is very fast. And you can do that for small binary chunks too. This is particularly important, for example, when you have coordinates embedded into your HDF5 file. These coordinates are typically much smaller than the actual data blocks because it's only a set of numbers along one axis rather than X by Y by Z. And so being able to pull those out into your references means that your load can be much faster. I have assigned here 2 examples, so I have some examples. This is what one of these saved set of references might look like. It's just a JSON file. So we can load this thing and we can look at one of the entries within it. For those that know what ZAR looks like, this is one of the metadata pieces, and it just looks like a little piece of JSON. So nice and straightforward. And this is stored in this global JSON file, which is a couple of 100 kilobytes. We can also look down the structure. So we have some references in here, and this indicates to us that this is a structured HDF file. You have embedded variables, and this is one of the arrays. And again, it has a bunch of JSON that tells you how to interpret the binary that you will be reading. And then here is one of those blocks of binary. In this case, this is the embedded form because it's particularly short. So it's stored as base 64. But most of them are like this. It's a reference, hence the name of the file system, to some URL, an offset, and a size. So what is this thing? This is a Ginger template. So we have a bunch of templates also defined in these references. And this is the actual location that we're going to be pulling from, which is a single massive HDF5 file. And this B key tells us that you can replace templates that look like this with this location, and then this is the offset and the size. So this forms all of these things together form a binary block. That was a slightly long explanation, but let's see it in action. Now let's see if Google will cooperate with me. This is an interesting one in that the location of the JSON file is on Google, but the location of the data is on S3, and this works seamlessly. I can plug all these things together in a single call to X-Array Open Dataset. This was my backup version if Google didn't cooperate. Having done that, I have a dataset. And this thing, I should probably have looked at how big is this thing. It's a fair size, a gigabyte in this case. It could be, I didn't actually download any data here. I'm just reading the metadata from the file stored on Google, and it tells me how to access all of the pieces that are stored on S3 and the access if I was to actually do some calculations. I won't do that now. All of that happens in parallel. I can draw these pieces of the original data set concurrently in parallel with Dask. And that's the example. So where does this all fit in? Well, I demonstrated HDF5 and ZAR. That's not the only place that this can work. For a start, there are many other file formats that have a similar scheme. You read some metadata, you figure out where the blocks of bytes that form arrays are. So array buffers, I should call them. This has already been done for TIFF in a project called TIFF file. You can scan a bunch of TIFFs and get one of these reference sets. It can be done for FITs, it can be done for dicom, it can be done for a whole load of different data formats that essentially have this same pattern. Once you've done the conversion and you've figured out these references, you don't need that third-party library anymore. So you scan the metadata just once, and then you can use ZAR, which is a very simple library to load them, or you can pass this consolidated virtual file system onto some other tool if you want to. There is a spec that is defined at this URL. I'll post that in Slack in a moment. And there are things that I would like to make happen for this in the future. We already support binary storage instead of JSON because the JSON references can get fairly large eventually, so you can store them using ZAR itself or Parquet. Maybe we'll enable lazy loading of those things. There's various things that we can do to try and make this more performant. Maybe we'll enable the conversion of types of file that don't expose their binary blocks. You have to download the whole file and read it with something to be able to interpret it as an array. Maybe we'll enable that. And maybe we'll have more complicated ways in which you can figure out where a target file and each of the chunks within it, where they fit into a global ensemble data set. That's it for my talk. And we can, again, discuss this at the end. So I'll just post this link and that's it. Oh, there's some questions here. We don't need to answer these now, but these are things that you might have thought of. This is sort of similar to some ideas that are around, but I would argue that it's far simpler and it enables us to access all this archival data using Dask and cloud things that otherwise we wouldn't be able to. So that's it.
I think you're up for another talk.
Yeah. Did you want to give a bee fact?
Sure. Okay. Honeybees communicate the location of nectar, pollen, and water sources with each other. Circle and audible signals. Interestingly, the orientation of the circle versus the waggle indicates the position of the sun, which the bees know they can detect the polarization of sunlight. All right, you're up.
Okay, this is the shorter one. So for those that don't know, FastParquet has been around for quite a few years. I started it as the first way to be able to load Parquet data into pandas. I was already at Anaconda at the time, and in the past couple of months, I decided to come back to it and renew it, given that the world of Parquet has moved on a little bit in the meantime, and it was time to apply some of that to FastParquet. So there's a whole bunch of these improvements. There is a tracking issue on GitHub that follows the progress that has been done and progress that is yet to come. So I'll just run through these bullet points and say what they mean. The first one, caching the lazy properties. This basically means when you open a Parquet dataset, a lot less work needs to be done. There's no need to compute various attributes if you're not going to access them. And this just means a general improvement in the performance of opening Parquet files. The second one, and this was a major rewrite, was to remove all of the dependency on number and replace it with Pythonized code. The performance of that code is essentially the same as it was before, but we no longer need the number dependency. And that means that the input time is faster, the install size is much smaller. And this makes FastParquet very competitive against PyArrow, which is quite a big install size. Thirdly, CramJam is a project which encapsulates several compression algorithms via their Rust implementations into a single statically linked library. FastParquet uses that instead of the several compression packages that it currently optionally depended on. Also, the speed is somewhat better because the main difference is that in Parquet, we always know for decompression how big that decompressed size is going to be, so you don't need to do multiple allocations. We now support the Parquet page header version 2, although it's not thoroughly tested yet. It's available. This has been around for a while and provides several improvements that I don't need to go into now. We can read datasets without this global metadata file, although the performance of this is not particularly fast. Previously, you had to manually go and find all of your files and pass them in a list. We support RLE dict encoding, which some people had noticed was missing because data in the wild already had this. Delta encoding also is an experimental. This is not in the wild as far as I know, but there is one example data set I managed to find which has it. So now we support that too. And you can install, now that we don't depend on number, you can install via wheels fairly well. We were bitten by the ABI change in NumPy, but aside from that, all seems to be working pretty well. Here's some quick benchmarks. The first couple are specific to my system. Your mileage may vary, as they say. So the input time has halved for FastParquet. Almost all of this 0.6 seconds is taken up by pandas. File open is also something like a factor of 2 better for a reasonably sized metadata blob. So if you have several files in your data set, then opening it will be faster than before. And then there's 3 benchmarks of actually data throughput here. You don't need to know the details. This is some custom benchmarking code. So the relative numbers here are important. And basically nothing got faster. Several things got considerably, nothing got slower. Several things got considerably faster through this rewrite. There are still things that I'm working on. These will come out in the next couple of months whenever I get time to do them, which is database v2 for writing, row level filtering rather than partition level filtering, various new types, and Pythonizing of the thrift metadata reader, which this last thing is a really considerable improvement in speed, but it will take a lot of effort to rewrite the code to use it. But I already have a prototype that at least does the actual parsing of the thrift metadata. That's it. Thank you.
All right, thank you. All right, next VFACT. For various reasons, worker bees will decide that their hive is no longer a suitable place to live. They create a queen supersedure cell to raise a new queen. The old queen dutifully lays a fertilized egg in the cell. When the new queen is nearly ready to hatch, a large portion of the bees will leave the hive with the old queen and swarm out of the hive to a tree branch, a parked car, with a window open, or any number of inconvenient locations. All right, Jacob, you're up.
Great, thanks, Dan. Hi, everybody. Yeah, I just wanted to talk to you about like a little side project I've been working on called Dask Control. So you can find this project in our reasonably new Dask Contrib org on GitHub. This is like a place that we created a little while back for putting projects that are maybe like incubating, or maybe they're community submissions that we kind of want to say, like, we as the Dask maintainers and the Dask like organization, we like this and we want to work on this, we want to contribute to this, but we maybe don't support it to the same level that we support the Dask core packages. So if you head to Dask Contrib, you can find Dask Control. I think it's the only project in there at the moment. And Dask Control aims to provide a set of utility libraries and things for controlling the lifecycle of your Dask cluster. So let me kind of dig a little bit into what I mean by that. Today, when you use Dask cluster managers to launch your Dask cluster, there's a very tight coupling between that Python function that you've instantiated and the actual cluster itself. So if you use local cluster in Python, you import that class, you instantiate that class, and that creates a bunch of Python subprocesses for the scheduler and the workers and all that kind of stuff. Right, this is great. It works well. If you use any of the other packages like Dask Kubernetes or Dask Job Queue or Dask Cloud Provider, similar things happen, right? We have code that represents the things that get created. In the case of like Dask Cloud Provider, often that's like a VM or a container or something. We have to speak to some cloud platform's API and ask for that VM to be created. And we have like a Python object that represents that VM, and we can kind of manage it from there. But what happens in the case where your Python process goes away, right? Whether you forcibly kill your Python process, maybe you restart your Jupyter kernel, maybe you throw your laptop in a lake, I don't know. Whatever you do to make Python stop and you lose all of that state, what happens to the Dask cluster? What happens to the resources? If you've used local cluster, then those are subprocesses of your Python process. The operating system will probably just kill those for you. If you're launching on an HPC system with like Slurm cluster from Dask Job Queue, those jobs will probably still exist on the cluster, right? Maybe they'll time out Dask, you might have set some idle timeouts within Dask, but if not, eventually you'll hit the wall time on the HPC, right? That job that you submitted, that'll time out. Maybe you'll just get told off by whoever manages that HPC if you've got some idle job running for 24 hours because you had a long wall time or something. But what happens in the case where there isn't like a cutoff kind of built into this? Maybe you're launching onto Kubernetes, maybe you're launching onto the cloud. Those platforms don't have a concept like a wall time. Those processes aren't going to get cleaned up. You're just going to have VMs hanging about on Google Cloud or wherever, running a Dask cluster for you. But you've lost that Python object that you used to create it. And that's not good because you can't at the moment get that back in order to scale it or delete it or use it or anything. You have to go into Google Cloud portal and kind of delete the VMs and clean up yourself, or you have to go in via kube control into Kubernetes and clean up the resources that you've got hanging over, right? So Dask Control is like some tools, but also like a bit of a spec for other Dask cluster managers to try and get around this. So ideally, if you create a cluster in Jupyter and you forcibly restart your notebook kernel, you shouldn't have to go manually clean up resources, and that's what we're trying to solve here. So the first thing you need, well, step 0 before this slide actually is each cluster needs to have a name or like a unique identifier, something that we can actually refer to this cluster as. We added that in distributed a little while ago actually. So now when you create clusters with local cluster or anything like that, it gets assigned like a name. It's just like a randomized UUID, right? But it gets given a name. So once you've got that, we need to be able to discover these clusters. How do I reach out and find my Dask clusters that I've made when I'm in a position of not knowing about them? And so to do that, you need to implement a Dask cluster discovery entry point using Python entry points. This is just a function which, I don't know, lists the running jobs on your HPC, or it polls the cloud platform, or it polls Kubernetes, and it says what containers, what VMs, what jobs do you have? Maybe look at some metadata. Are any of these a Dask cluster? Oh yes, this one's a Dask cluster. I know the UUID. That function should then return like a list of UUIDs, and ideally the cluster manager that created that. Once we've got discovery implemented, we then need to be able to reconstruct that Python object that represented that cluster. Now, Dask control, once it's called the discovery method, it will then try and call a new from name class method on the cluster manager that created it, and pass in that name or that UUID to say, can you reconstruct me an object that represents this cluster that already exists, that we already have VMs for, we already have jobs for. This is not implemented in basically all of the cluster managers today, but this is kind of where we're trying to head to with this thing. Like, this is what I mean. It's like a spec of how to implement this kind of lifecycle stuff. But once a cluster manager does implement from name, I think Helm cluster in Dask Kubernetes does implement this today. We can then reconstruct that object, and we can treat it as if we'd made it within the current Python session. We can scale it. We can pass it to a client object to connect to it and use it. We can call adaptive if it supports adaptive, and it will start adapting. And more importantly, we can delete it. So if you've spun up cloud resources, you can then spin down those cloud resources. Now, to give you like a little insight into the code that exists today, if you pip or conda install Dask control, there's a whole bunch of lifecycle methods that you can grab, like list clusters, get cluster, scale cluster, delete cluster. And this, under the hood, calls all of the registered discovery methods, grabs the clusters, recreates their objects, and then performs whatever operation you've asked to on there. So here's an example of calling list cluster. There is like a reference implementation at the moment in Dask control, which just looks on your local machine at all the open ports and has a prod at them to see if any of them are a Dask cluster. And if so, it makes this other representation called a proxy cluster, just because you can't actually recreate a local cluster, because the local cluster has subprocessors and things. But we have this proxy cluster. You can treat it like a cluster manager. You can pass it to a client. You can do everything you like with that. But we're slowly going through and implementing these in other cluster managers too. But once you've got this Python tooling, we've also been able to implement a command line utility. So you can do like Dask control cluster list, and it'll give you a list of all of your clusters. You can call cluster scale and tell it, which cluster you want and how many workers you want. And you can kind of interact from the command line with it. And more importantly, you can call Dask control cluster delete and clean up your resources. This is great if you're trying to create clusters as part of like a workflow engine, or maybe you've got maybe you're using something like Airflow where you've got stages where you want stage 1, create a cluster, stage 2, connect to it and use it, stage 3, maybe connect to it and do something else with it, and stage N, delete it again, right? So being able to like separate all this stuff out allows you to be a bit more flexible in your Dask like lifecycle management. So just to wrap up, the next steps for this project really, kind of where we get time to work on it, is try and implement this spec in as many cluster managers as possible. I've been focusing a bit on Dask Kubernetes. I'm looking forward to getting to working on Dask Cloud Provider with this. It'd be great to see this in JobQ and Dask Yarn and other places. Now, the Jupyter Lab extension has the ability to list clusters that you have access to that it has created, but it would be great to like pull those pieces out of that and put in the discovery, so that when you're using Jupyter Lab with the Dask extension, your cluster list on the side will not only show the clusters that it's created, but also any others that it can discover on your network, which is really helpful. If you like deploy Dask with the Dask Helm chart, you get Jupyter Lab and a Dask cluster. And those two things aren't quite linked up at the moment. You have to like know that there's a Dask cluster. So it'd be great for that to just appear on the side. Oh, you've got a Dask cluster that came out of the box with your Helm chart. And the last thing to do really is to get things nice and stable and then move it up into the Dask org. Hopefully it'll be one of the first projects to kind of go through that transition. So thank you very much. I hope that wasn't too long. If you've got any questions, please ping me on Slack. You can go and find the documentation and all the code on GitHub. So thank you very much.